Okay, so today we're going to use what we know about rigid bodies to get into linkages. So this new topic is linkages. And linkages are collections of rigid bodies connected by joints that move. If they don't move, a collection of rigid body connected by joints, what's that called? The people in statics. Yeah, exactly. If it doesn't move, it's a structure. So I'm going to just give you sort of an outline of the approach, and then we'll get into some examples. These are pretty time-consuming problems because you have to do the rigid body analysis for every member in the structure, in the linkage. So here's the approach. Oh, and by the way, well, we've only done rigid bodies in 2 dimensions, so it makes sense that we'd only be able to do linkages in 2 dimensions so far. Does anyone remember, have I given any kind of illustration of why we can only do stuff in 2D with the approach that we're using for rigid bodies? Do you remember seeing anything like that?
The homework problem where it had one moving in one direction.
No, that's a little bit different. Why can we currently only do rigid body kinetics in 2D? Okay. Well, let me give an illustration of, okay, well, and before I write this, the main equation in rigid body kinetics is rotational Newton's second law that says add up all the moments. That's equal to the moment of inertia times the angular acceleration, right? Okay, so let's think about what happens as an object moves in 2D. So at instant 1, let's say this object starts out like this. And then at instant 2, it ends up like this. Okay? It's just rotated 30 degrees or whatever. But the key thing is, notice that the moment of inertia is the same in both of these 2 orientations.
I think you did talk about it.
What?
I think you did talk
Okay.
about it.
Okay, yeah. Well, no one remembers well enough to tell me what I said, so we'll talk about it again. It's quick. In both orientations. In 3D now, there's a whole different set of motions that are allowed. So let's say at instant 1, we have an object like this. And at instant 2, we have an object like this, okay? In 2D, okay, so in order to think about this, you have to think about the axis, you have to think about an axis of rotation. So here, in 2 dimensions, our only axis of rotation is, you know, out of the page. Okay, so this moment of inertia is a moment of inertia about that vector pointing out of the page. What? Yeah, exactly. But now think about the same thing here and think about the moment of inertia of a vector, you know, out of the page, basically. Here we have one formula for the moment of inertia. Here we have a totally different formula for that moment of inertia. Okay, and so I changes instant to instant. And so what do you use for I in the moment equation? Okay, and so that's the fundamental problem here. You just can't use that equation in 3D. So with this approach, we can only work in 2D. Okay? All right, so now linkages. So here's a general approach to linkages. And the linkages, for the same reason above, has to be in 2D. So first, do the rigid body analysis for each of the rigid bodies that make up the linkage. So I'll say the rigid body kinetics steps for each rigid body in the linkage. Once you're done with this step, you'll have more variables than equations. Which means you need more equations without introducing more variables. Okay? So we'll need more equations. And these are going to come from constraint equations. So the constraint equations, at any pin joint between bodies, and I'll call the pin P, that connects two rigid bodies, we're going to require that the acceleration of P according to body A, you know, the first body, or let's say body 1, has to be equal to the acceleration at p according to body 2.
P lowercase or P uppercase?
I don't know, it doesn't matter. That just represents that pin. Okay, so what we're saying here is, intuitively, we're just saying that the two points are connected at a pin joint. And we're saying that them being connected means that the acceleration of this part that's connected to it has to be the same as the acceleration of this part that's connected to it. Otherwise, they're flying apart. Okay? If the body has a fixed point, we'll calculate that acceleration as, so the same way we calculate accelerations of points always on rigid bodies. It's a circular motion about the fixed point. So all right watermelons will rot. If the body has no fixed point, then we're going to use that the acceleration of p relative to the ground is equal to the acceleration of p relative to the center of mass plus the acceleration of the center of mass relative to the ground. This one comes from a vector variable or multiple scalar variables from our rigid body kinetics. And this one comes from the watermelon equation. Okay, so that's the approach anytime you have a pin joint connecting two bodies. And then the other kind of constraint you can have is if a point on a rigid body slides or rolls along a known path, then the part of the acceleration of that contact point that's perpendicular to the path is 0. Okay, so I'll get into both of these two. Let me draw a picture of what I'm talking about here, though. So let's say that we have a body. We don't know what the rest of the linkage is doing, but let's say we have a pin in a slot here. Okay. So there's a whole linkage. We've done all the linkage stuff. what can we say? And let me call this point P. Okay, so what do we know about the acceleration of the point P? We know that if we calculate the acceleration of this using relative motion and the watermelon equation and whatever, it can't move perpendicular to that slot. So we can figure out the component that's perpendicular to that slot. Usually it's just going to be either an X or a Y component, but you also could do it as a dot product. We'll do some examples like that. Usually it'll just be a matter of setting the X component equal to 0 or the Y component equal to 0. But anyways, calculate the acceleration at this point and then set the perpendicular part equal to 0. Okay, and if you do it right, then the number of constraints that you get will exactly equal the number of new equations you need so that you have the same number of equations and variables and you can solve the system. Okay? So for the simplest example possible, let's say we have this body connected to the ground by a pin, and then it's connected to this horizontal body. Let's say that the lengths of each of these are 0.5 meters, and the masses are 2 kilograms. And I'll number these. Let's say that at this instant, omega 1 and omega 2 are both equal to 0, just to simplify this as much as we can to start with. And then I'm going to apply a force at the midpoint of this one, this way, of 20 newtons. And we want to calculate the angular accelerations of the bodies. Okay? So the steps are, the first step is every rigid body in that linkage. You're just going to go through the rigid body kinetics analysis. You're going to go through the 6 steps. So this step 1 looks short, but obviously that's a pretty time-consuming one if you have a whole bunch of members. So I'm going to start with member 1. Does member 1 have a fixed point? Yes. It's fixed to another body, but it's not fixed to the ground. Okay, like you could, the question you have to ask yourself is, as this linkage moves all the ways it can move, is that point on that body going to stay fixed compared to the ground? You see what I mean? I mean, this thing can move, this thing can move, that point can move all over the place. Okay. I mean, I guess it can move in a circle.
Oh.
So no fixed point. And so what's our about point going to be?
The language.
Center of mass. So the about point is the center of mass. And so now we can calculate the moment of inertia. So the moment of inertia for body 1 is equal to 1/12 times the mass times the length squared. And that is 1/24. So 0.0416 repeating kilogram meters squared. Now free body diagram. There's a weight force down that's equal to 2 times 9.81, so 19.62. And then at this pin joint, there's an unknown force vector. I'm going to use the naming convention force on body 1 by body 2. Okay? Anybody have any questions about that? This naming convention is really, you pretty much are going to need to do this on these linkage problems.
So the force is going both sides?
What?
Is going.
Yeah, we don't know the components, right? Each one of those represents a component. That, you know, it's the same thing that you've done with pin joints in the past. It's just that now it's, this is connected to another body, and that's why we're using this subscript notation.
But that is not a fixed point.
It's not fixed. It's fixed to another body, but a fixed point means fixed in our coordinate system, fixed to the ground. Okay? And now we'll go to the table. The first force I'll do is the weight force. What's the vector from the about point to where the weight force is applied? 0, yep. And the force is 0, negative 19.62. And the cross product is 0.
Well, how's the position 0 when it's in the middle?
Because you have to remember the definition of the row vector. The row vector is a vector that goes, the tail is at the about point, and the head is at where the force is applied. The about point is the center of mass. That's the same place.
Oh,
Yeah.
yeah.
And now we'll do this force F12. So what's the row vector? What's the vector that goes from the center of mass to where that F12 is applied? Yep. So 0.250. And the force vector is F12x, F12y. The cross product is 0.25 times F12y minus 0. Okay? Any questions about that?
Are we also saying that 2 on 1?
In this class, we're gonna, so are you saying like just the notation? Could you instead say by 2 on 1? don't do it in this class. You'll get so confused. But yes, you can. It's sort of an unfortunate fact that that about half of the world would call this the force 2 applies to 1, F2-1, and about half the world would call it the force on 1 by 2. Too bad. Like that is really a pain in the butt. But so we're just going to have to choose one, you know. And really, it seems to me, from what I can tell, that engineers tend to do it the way we're going to do it in this class, where the body that you're isolating is the first subscript, and physicists tend to do it the other way. Okay. So I think this is a more common way to do it in engineering, but it would be very nice if this was standardized. You just have to, whenever you see a subscript notation like this, you have to be extra sure that you know what they're referring to. In this class, this will always mean the force on 1 by 2.
Not 12.
Not 12 either. Okay, any other questions? Okay. There is no fixed point, so do we need Newton's second law or not? Yep. So Newton's second law says 0, negative 19.62 plus F12x, F12y is equal to the mass times the acceleration of the center of mass. I'm going to just call that A1x and A1y. So this vector is the acceleration of the center of mass. That's what I'm referring to. But the only A variables we are ever going to have are going to be accelerations of centers of mass. So you could just use the number of the body whose center of mass you're calculating there. All right, so we get two equations out of this. The first one says F12x minus 2A1x is equal to 0. And the second one says F12y minus 2A1y is equal to positive 19.62. Why did I rearrange this into this format where I have all my variables on the left and all my constants on the right? Yeah, because when we get to this big system of equations at the end, we're going to use reduced row echelon form to solve it. So now we'll go to the moment equation. And that says 0 plus 0.25 F12y is equal to the moment of inertia times the angular acceleration of body 1. And that gives us our third equation. And I'll write that as 0.25 F12y minus 0.0416, repeating, alpha 1 is equal to 0. Any questions about that first body? Well, where are we for equations and variables? We have 3 equations. For variables, we have F12, A1, and the single scalar alpha 1. So that is 1, 2, 3, 4, 5 variables. Each one of those vectors is two variables, an x and a y component. So we can't solve for anything yet. And now, even if we could, I mean, I would say just plug along, follow the same method every time. Don't look for new stuff. Just go through the rigid body kinetics of each body and then get to the constraint equations after that. So now we're going to, that was body member 1. Now we're going to member 2. And well, let's go through the steps. Getting sloppy. Does member 2 have a fixed point?
Yes.
Yes, fixed point at the bottom.
Can you go one line up, please?
Yeah.
Thank you.
So it's fixed at the pin to the ground. So that's the about point. And so the moment of inertia of body 2 is, we're going to have to use the parallel axis theorem. So this is 1/12 times 2 times 0.5 squared plus the mass times the distance squared from the center of mass to our actual about point. The mass is 2. What's the distance from the center of mass to the about point? 0.25 squared. And so that is 0.16 repeating kilogram meter squared. And now free body diagram. We have the weight force. I'll do it like this just to clean up the picture a little bit. So that's 2 times 9.81, 19.62. And then we have the horizontal force of 20 newtons. Up here, we have the force on 2 by 1. Okay, but if we called it the force on 2 by 1, that would introduce new variables. Instead, what we want to do is use Newton's third law and recognize that this is negative F12. Okay, it's the negative of this vector variable we've already defined. Then down here, you could call this the force on 2 by the ground, or when it's connected to the ground, you don't have to use that subscript notation. So I'm just going to call this R, just a reaction force with the ground. Anybody have any questions about that free body diagram?
Okay, so for R, we don't have to take into account for the bar that's above it.
That's right. It does come into it, but it'll do that itself on the equations.
Okay.
All you have to think about is apply the weight force, and then just go around the boundary of this and look for where the boundary is directly in contact with the other things.
So in a linkage problem, whatever's connected to the wall or the ground, for example, is going to you can just write R.
Yeah, that's right.
Then the other point is going to have to involve
That's right.
the other body.
Exactly. That's exactly right. You could call this the force on 2, the force 2G, but really the only reason we use that subscript notation is so that we can use Newton's third law. And when it's connected to the ground, we're never going to isolate the ground, so it'll never come up, Pedro, did you have a question?
The 19.62 is the mass, right?
Times gravity, that's right.
Why did you put not the 20 and then like points at like 6.2 like in the middle of the second? Why like in the free body diagram, why did you draw that vector?
Oh, yeah. Well, the weight always acts at the center of mass of anything. So that's why the weight is there. And then the 20, that's just where that force is supposed to be applied.
Oh, is that for, okay, never mind. I was actually, I thought that was that 19.62.
Oh, okay.
It was like the other
I see.
linkage going.
That's just supposed to be an external force, like someone hit, like what's this thing gonna do if it starts at rest and you give it a tap with a hammer?
Okay.
What's the acceleration gonna be?
And so that 19.62 is the mass for that second body.
Yeah, times 9.81.
Okay. I'm just a little lost.
That's okay. Yeah, this is, we'll get a lot of practice with these. Any other questions about the free body diagram? So now we're going to go to the table. I'll start with the weight. Actually, let me start with R. And I'll just work my way up. Okay, so the about point is at that pin at the bottom. So what's the row vector from the about point to where R is applied?
0.
0, yep. So 0, 0. The force is Rx, Ry. Cross product is 0. Now I'll go up to the weight. What's the row vector that goes from where R is applied to the center of mass? Yep, 0, positive 0.25. And the force vector is 0, negative 19.62. Cross product is 0. And then the 20. Yep, same row vector. And the force is 20, 0. Cross product is 0 times 0 minus 0.25 times 20, so that's negative 5. And then the last one is the negative F12. That row vector is 0.5. The force is negative F12x, negative F12y. Cross product is positive 0.5 F12x. Any questions about that? Since there's a fixed point, there's no Newton's second law. And so we'll go to the moment equation. And it says negative 5 plus 0.5 F12x is equal to our moment of inertia times the angular acceleration of body 2. And I'll rearrange this, and this will be, we had 3 equations from body 1. Now we have a 4th equation that says 0.5 F12x minus 0.16 repeating alpha 2 is equal to positive 5. Okay, and now let's do the same thing we did before, figure out how many equations we have, how many variables we have. We have 4 equations. What about variables? Well, we already had these 5. Our new equation has F12x, which we already had, and it has alpha 2. So now we have 6 variables. And these are F12, A1, alpha 1, and alpha 2. I want to point out one thing. We would be thinking